Okay, good morning, everyone. And you should be looking at my screen at this point with at least me over in the right-hand corner. You may have a few other people along that side if you're in gallery mode. If you want to go into speaker mode, you'll just see me. And you are all muted, but you can unmute yourself. I ask that you don't. The only person that's going to be unmuted besides me is Greg Valero, who helps me with the questions from time to time. But if something does absolutely have to be said by you before I unmute everyone at the end of class, then you can do that. But better that there's no background noise going on from all your different homes while the class is going on. So welcome to quantum theory. You can see the cartoon over on the left is a reference, of course, to Heisenberg uncertainty principle, and the bottom right is the famous Schrodinger equation. We, of course, won't be solving the Schrodinger equation, but we will be talking about it and talking about what it means and what kind of information we can draw from the solutions to the Schrodinger equation. So, and two very, very famous quotes about quantum mechanics, which I'm sure some of you have heard before. One is from Bohr, that anyone who is not shocked by quantum theory has not understood it. And Richard Feynman saying, I think I can safely say that no one understands quantum mechanics. Okay, let's start with a little bit of context, if I can. Our course objectives are two, basically. One is to study the structure and properties of atoms. That is going to be our focus. We're going to stay on the atomic level and look at the quantum atom, very different from the atom that we learned in high school chemistry. We know basic things, remember, from a million years ago in high school chemistry, that atoms are made up of a positive nucleus with negatives surrounding electrons. Notice I don't say orbiting, just kind of vaguely surrounding. They combine to make up the physical world as we know it. This is of course, the foundation of all of chemistry. They create light and all of its properties. Some of them are unstable, given the name by Marie Curie of radioactivity. Very interesting property of atoms, very important property, one that as we study it, we'll learn a lot about the atom. And it can be split and fused. Atoms can be pulled apart, broken apart, and they can be fused together, which is a process that can release enormous amounts of energy beyond any other energy source that we have in the universe. And also these constituents that we're going to focus on, okay, the nucleus, the proton, the neutron, and the electron. These are really the only enduring members of those fundamental particles which have been given all the attention and all the pizzazz and all the information on the popular press for generations. Particle physics, not to diminish particle physics at all, but in fact, those things don't last very long. They're around for microseconds or less. These are the only three objects that really endure and create the world, the universe as we know: the proton, the neutron, and the electron. And that's one reason why in this course I want to focus on those three objects and what we can learn about them on the quantum level. The other objective we're going to have is to look at some of the modern technologies that are based upon quantum theory and the quantum atom. Nuclear energy, lasers, solar cells, and photomultipliers, the whole industry of semiconductors, which basically is our modern world, nuclear chemistry, the various scans, medical scans that we use, MRIs, PET scans, electron microscopes. Two reasons why I'd like to focus on these towards the end of the course I think they're interesting, of course, in themselves. These things basically make up the building blocks of our modern world, but also it's another window into the working of the atom, working of the quantum world, by looking at how they're used to build these kinds of technologies to do useful things, we get another kind of insight as opposed to the purely theoretical understanding of quantum mechanics, of just what some of these quantum properties mean by seeing how they're used in applications. So I thought for those two reasons, it's worthwhile for us to spend some time on those technologies. One of the big things we're going to do in our course here, guys, is we're going to lose our physical model of the atom, the one that we've been carrying around in our heads, certainly since elementary school, confirmed in our high school chemistry class. We all recognize the picture up on the left. That's an atom. It's the famous logo of the Atomic Energy Commission back in the day. It's been folded into the new the Department of Energy. This was actually closed down in 1975. But it's interesting, this thing was set up right after World War II, and it used this logo, right, in 1946 when it was set up, and it continued to be used until it was closed down in 1975. And this icon is still used today to depict the atom. It is the most familiar physical model of the atom that we have. It's universally recognized. Okay? It's in fact a particular model of the atom. This atom model goes back to 1917. It's the Bohr-Sommerfeld atom. And in fact, it's the next to last literal physical model of the atom that has ever been put forth. Yeah, there'll be one more. We'll look at one more physical model of the atom beyond this one. And that's the last one that's been ever put forth. It was put forth in the early 20s. And now we really don't have a literal physical model of the atom anymore. Quantum mechanics doesn't allow us to draw one. Oh, there are plenty of physical models, okay, of the atom, many, many different kinds. But these are not literal physical models. These are scientific models which help us explain one or two or three different properties of the atom. They're very, very useful, but they're not meant to be taken literally as truly what atoms look like. And there, you can see there are many, many of them when we're after different kinds of properties of the atom. Different models will help us explain some properties better than others. But that picture up on the top left, yeah, that's our next to last picture of the literal physical atom, the planetary model of Bohr, and it is not true. There's almost nothing true about that picture, as we'll see. I'm sorry, am I going the wrong way? I was going the wrong way, sorry. Okay, so just to drill down a little bit more on these questions, what is the fundamental structure and properties of matter? Matter made up of atoms, matter made up of protons, neutrons, and electrons. An age-old question is, what is the nature of matter in its most fundamental form? Do we live in a bucket of molasses or in a pail of sand? As you cut down, break down a piece of matter finer and finer and finer, what will happen eventually? Will you eventually get down to something which you can't cut at all, or will this just be able to be done theoretically ad infinitum? Okay, going back to the speculations of the ancient Greeks. We know somehow or other that the answer to this question, what is the fundamental structure and properties of matter, are in that diagram, in the periodic table. That's where the answer must lie, in this incredible table of all the elements that make up the universe. Why does this table exist like this? Why can this tell us so much about the properties of matter? What are those columns that have all the same color? Why are these atoms put in this way, having all these similar properties? What is creating this kind of incredible, elaborate structure? There must be some explanation for. Matter of fact, the explanation of this must be the key to what the fundamental structure and properties of matter are, if we can understand the periodic table. And the periodic table, as we'll see, was developed long before understanding what it meant and why it was constructed the way it did. The chemists were able to put the elements in a structure like this where elements of common properties could be in the same column. That you can do by just knowing the properties of atoms. But why? Why does it create such a structure like this? That's something that was not understood until the quantum theory. This is one of the great objectives that we have in our course, is to understand the periodic table. If we can understand the periodic table, not only will we understand a lot about quantum theory, we will truly understand the fundamental structure and where the properties of matter come from. Another important property of matter is that it creates light. Newton showed us that white light is actually sunlight, is composed of the various different colors, broke that up with a prism. But you know, when you look at sunlight even more carefully, you can see that not only is in sunlight do we have visible light, but there are other wavelengths of light that come from the sun. There's ultraviolet light, there's infrared light. And if you wanted to make a graph of just how bright these different wavelengths were, you would get the graph like this. This is called the solar spectrum. And what that red line is doing, that line graph, is showing you how bright those different colors are. You can see on the extreme left, it's the intensity of the light. You can see that sunlight, its most intense, its brightest, is in the visible region, not surprising. That's evolution in reverse, because the sun puts out light at this particular band, being its strongest, its brightest. That's why our eyes have adapted to be. This is why it's across the visible spectrum. So light does peak. The brightness of sunlight does peak in the visible spectrum. Peaks are in the yellow, green area of the visible spectrum. But there is plenty of light coming from the sun at other wavelengths that we can't see. And this graph, again, is something very intriguing. Why is it that the sun creates light like this? Why does it create these various different colors? And I use colors now in its broadest sense, colors in the sense of the wavelengths or the frequencies of light, even the ones that we can see. Why in this particular breakup of brightnesses? Why does the sunlight peak in the yellow-green section of the spectrum? Why does it fall off as we get to higher frequencies in the ultraviolet? Why does it fall off when we get to lower frequencies in the infrared? And why does it fall off just the way it does? And does all light, if I turned on any light at all, if I turned on a light bulb, for example, would I get the same basic kind of graph? Or do different lights produce different kinds of distributions of the colors in their different brightnesses? Can we understand this? Because what's doing this are atoms. Atoms are making this happen. And it gets even more intriguing, because if you take pure atoms, pure elements, and excite them, bring up their energy, they will glow. And in fact, different elements will glow in different ways. They will produce, to our eye, a composite different color. What's even more intriguing as the light, when we analyze coming out of these various different pure elements, don't look like the spectrum on the left-hand side. Not all the colors are there in different brightnesses. In fact, when we break up these particular lights into a prism, we'll get individual colors. Now we're just looking at the visible spectrum. We're just looking at the colors that we can see. These elements, when they glow like this, give off also ultraviolet light and infrared light. But let's just focus for a moment on just what we can see. And that top bar of those four colors, that's called the hydrogen spectrum. Those are the four visible colors that are produced by glowing hydrogen, the most famous spectrum. What's most striking about that spectrum compared to the one on the left is that it's not continuous. Not all the colors are given out, only four. This is very strange. Why these four colors? Why is it that hydrogen produces these four colors? What does it say about the element of hydrogen? It must be saying something very profound about the structure of whatever it is that makes up hydrogen. And of course, the various different elements create different sets of colors. So we must be looking at different structures of different elements. Why these colors, and why only particular colors? What happened to the continuous spectrum of sunlight? A number of just very, very intriguing questions that, was part of classical physics of the 19th century, which could not be answered, could only be answered finally coming into the quantum revolution. Another interesting thing I say about light before we leave this idea, and that is that, only atoms create light today in our modern universe, the universe of today. There was a short time, according to the Big Bang Theory, when the universe first came into being, and we had this tremendous, whatever you want to call it, singularity developing into the great ball of energy, of pure radiant energy, and the creation of matter, beginning with the quantum particles and expanding out. Yes, during that very, very short time, there was light, there was radiation. And as the universe expanded and cooled over a relatively short period of time, just 380,000 years, the Big Bang Theory says, this radiation did exist. There were no atoms. It was only a plasma, just loose particles, loose protons, neutrons, electrons, and other kinds of various subatomic particles. But finally, after 380,000 years, the universe expanded and cooled enough where atoms could form. And that radiation that had been in that Big Bang for all those thousands of years finally was released in the cosmic microwave background. But the atoms that were left, mostly of hydrogen and helium, those atoms did not produce light. They didn't have enough energy to produce light. It took another hundreds of millions of years before these atoms could form again by gravity to start the process of fusion to create protostars. We went for 400 million years of the beginning of the universe with no light except for that cosmic background radiation that was created at the very, very beginning. Only after that, only when we began to get protostars, finally did we get new light brought into the universe by the protostars and the stars going forward. And ever since then, the only things that produce light are atoms. How do atoms produce light? How does it produce it in these different ways? One of the great questions that we'll be able to answer in our study of quantum theory. And radioactivity, a very important property of atoms, something that we really wouldn't be able to understand the atom unless we can grapple with radioactivity. Why is it that some atoms are inherently unstable and throw out pieces of each other in terms of matter or radiation? When we look at all of the elements that we know, and we can see that we know they're made up of protons and neutrons, okay, in their nucleus. Here we have a graph of the number of protons on the y-axis, the number of neutrons making up an atom in the x-axis, and the green bars, those are the stable atoms. Those are the atoms which have that number of protons and that number of neutrons, are nice stable atoms, okay, that can last indefinitely. The yellow boxes are also atoms. They're also combinations of a certain number of neutrons and protons in the nucleus, but they're radioactive. They're unstable. You can see that as the number of protons and neutrons grow, that there's generally more neutrons than protons. You can see that the graph kind of bends down away from the line where the neutrons are equal to the protons. So where we find atoms is where there are more neutrons than protons in the nucleus. Why is that? And why are some atoms stable, the green combinations of neutrons and protons, and some atoms are radioactive? They're unstable, all the rest, the yellow. And very intriguing, why is it that after lead, atomic number 82, 82 protons, there are no more stable electrons, stable atoms. All atoms above atomic number 82 are inherently unstable. Perhaps the most famous one is 92, uranium. Thorium, number 90. All of the atoms which have more than 82 protons are inherently unstable. Why? Very many intriguing questions that we will grapple with and be able to understand as our understanding of quantum theory grows. These things were not understood, not able to be understood without the quantum theory. Nuclear energy, atomic energy, where does the source of such energy come from? An important question. So to finish off our idea of context here, we want to look at the two great pieces of physics. One is the classical physics, and its two great pieces, the Newtonian mechanics and electromagnetism, the two pillars of classical physics of the 19th century. And they in turn created, with their great synthesis on the Newtonian mechanics side, we have the theory of heat and thermodynamics, and electromagnetism finally synthesized for us our understanding of light as a wave theory. And this is classical physics by and large. And we'll need to understand some of this to understand the revolution of quantum theory, because of course it came from people trained in classical physics. Modern physics also has two big pillars, general relativity and the quantum theory. Quantum theory further can be broken down into atomic physics, nuclear physics, and finally the one that gets all the attention, that has been getting all the attention in the press for generations, particle physics. But our focus, as I say, will be here. We're going to focus on this level of the quantum revolution. Just a nod towards the standard model. Yes, there are objects below the atomic level. Right? There's the quarks, which make up protons and neutrons, the lepton family, which the electron is one of, and the force particles, which are part of particle physics of the modern quantum theory. We're not going to have to delve too much into this because we're going to stay on the atomic level. This is a different course. This is an entirely different course to look at particle physics. Okay? But I do want to just make a mention that yes, protons and neutrons are made up of two kinds of quarks. The first two that were discovered, the up and the down quark. Two ups and a down make a proton, two downs and an up make a neutron. And we have the electron. I said that these are the only particles, the proton, the neutron, and the electron, which endure in the universe. Okay, there are many other, there's the particle zoo discovered in the 50s and 60s, yes, they're all there, they all exist. They exist for microseconds or less, okay? But these particles endure. Maybe to be fair, the other particles that do endure would be the neutrinos. The neutrinos down here at the bottom of the lepton family with the electron. Yes, they do endure, that is true. They don't do anything except move around undetected. They don't seem to have much of a use except in certain equations to satisfy the conservation of energy. So that's good. But yes, they do endure, but they don't really do anything for the world of matter and chemistry on the level that we're concerned with. So again, just to look one last time at that video that I asked you to watch in the beginning about the sizes of things that we'll be talking about. I just want to emphasize that it would be very helpful to get a feel for the incredible small sizes of things that we'll be talking about. If you lose that, if you just take it for granted, you will lose some of the incredible awe of on the level that we are studying things and how we can know things at this level if we kind of lose sight of them and take them for granted. So I'd just like to emphasize it one more time, the scale that we'll be talking about. On the angstrom scale, the old-fashioned 10 to the minus 10th meter scale, 1/10 of a nanometer is the atom. The nucleus size 10,000 times smaller. The proton 1,000 times smaller than that. And finally, if you can say this at all, if you can talk about size at all at this level in a meaningful way, the quark and the electron seem to have a size of about 10 to the minus 18. Going the other way from the electron, we can say that the proton is 1,000 times bigger in volume, in radius, I'm sorry, in radius, not in volume, in radius than the electron. And the nucleus is 10 times bigger than the proton, going from 1,000 to 10,000 is 10 times bigger. And finally, the atom itself is 10,000 times bigger radius than the nucleus. So try to keep these numbers in mind, and also if you can, particularly if you like numbers, try to become comfortable with numbers like this and writing numbers this way. That reminds me of the data sheet that I sent out in the Wednesday email. I'm sorry, I sent out the second page, which I didn't mean to. This is something that I started in last term's course on cosmology, and I thought it was useful. Some people liked it, people who found it useful and interesting. The second page is really the beginning formulas of the cosmology course. So I apologize. I didn't mean for that page to get still stuck in there at all. But the first page is kind of our beginning of our data sheet for our course, and it has the prefixes of the various powers of 10 that we'll be using, kind of handy to take a look at. And just some of the numbers that get us started, the ones that I just mentioned, sizes of atoms and nucleuses, and of course light. The speed of light, interesting number, and the size of the wavelengths of the extremes of visible light, red light, and violet light. Notice they are in the hundreds of nanometers, much, much larger. The wavelengths of visible light are much, much larger than the sizes of radiuses of the objects that we'll be talking about, atoms and below. Okay, we will be talking about a revolution. Here's a revolution, the most famous one probably, the classical scientific revolution. Relatively straightforward story. Of course, this does not show everything, but if you were to cover these people and their accomplishments and their discoveries and their theories in this kind of order, you'll easily get about 80% at least of the scientific revolution. Not so much for the revolution that we'll be trying to tackle here, the birth of atomic physics. Not as simple a story at all. It is, in fact, as you can see, not a linear story. Let me take you through this a little bit, because this kind of will recap at least the first half of our course to bring us up to the discovery of quantum theory. We see at the top, basically, 19th century physical science. That's where we begin. And the atomic hypothesis is the first thing that we will tackle, leading to the periodic table. We will begin in the 1895 area with a cascade of incredible discoveries that really bring us from the classical period into the modern period. The discovery of X-rays, the electron, radioactivity, and the transmutation of elements. Elements can simply change from one element to the other spontaneously through the expulsion of pieces of itself, turning itself from one element into another. Going back to the chemistry side, atoms finally will be established for all to finally agree with. You may be surprised that it took a while. It took until the turn of the century for, it was some of the chemists who were the last people to be dragged kicking and screaming into the world of truly believing in the actual reality of atoms. Oh, it was a very useful model. They had no trouble using it as a model to explain their chemical behavior, but they didn't necessarily think that they were real. It was just a useful model. It was the physicists who actually began to believe in atoms much earlier, looking at their physical theories than the chemists. But finally, we do get the atoms established, and I'm hoping that we will get through this part of the story today, get through the establishment of atoms. This is what our presentation will be focused on once we get finished with our context here. We then go to the Rutherford nuclei atom, the discovery of the nucleus itself. And then with the power of X-rays and with atoms established, we finally get the true meaning of atomic number. A very important development, a very important discovery, that the atomic number is the number of positive charge in the nucleus. Notice I didn't say protons yet, but it is the amount of positive charge in the nucleus is the atomic number, wherever that atomic number comes from. And the last piece of our puzzle is the quantum hypothesis itself, going back to that spectrum of the sun and trying to understand that distribution of not only colors, but the various brightnesses, the intensities of those colors. We'll begin here with the quantum hypothesis. With all those pieces together, will bring us to the Bohr quantum atom and the limitations, the problems of the Bohr quantum atom. What the Bohr quantum atom couldn't explain brings us to quantum mechanics and our modern ideas of atomic and nuclear physics. So this is where we'll be going for at least half our course, taking us into the realm of the quantum theory. And we'll spend some time trying to understand quantum theory without a heck of a lot of mathematics. We'll be using analogies and models as best we can. I'll be trying to explain some of the math on a level that is right for us, but we certainly will be using models and analogies to understand quantum mechanics. And as we move along, we'll go through some of those applications and technologies that grew out of this understanding. Okay, so let's begin. Before I do, could I ask Greg? Greg, do we have any questions for us on the chat line?
Yes, we do, Peter. Excuse me. Jim Talbert asks, if particle physics is both more fundamental and more discussed in popular physics, why are we stopping one level above that?
Because I chose to teach a course on the atom. Particle physics is a wonderful, powerful subject. It is the modern cutting edge of physics, but it is a different subject. It requires the understanding of the quantum theory. This course here would be a very nice intro then to go down the level of particle physics, but it truly is a different subject. And I only have 8 classes, and I wanted to do justice to the topic that I did want to discuss, and that was on the atomic level. So if there is a great interest for us to go further in this study and to then look at particle physics, I'd be very, very happy to do that in a different course.
And then, Peter, I have a question. Can any significance be applied to the fact that neutrons, protons, and electrons are 10 times bigger and smaller depending on which way you go, that they're equally 10 times, have the ratio of 10 times bigger or smaller?
That's a good question, Greg. I don't know. I've never seen anything like that, that there's really, the factors of 10 are inherent in the properties of these objects. So I would say my guess is no, that's not some truly inherent property of these guys. Okay, I forgot to mention, if you do have any questions, please write them down, put them in the chat. Make sure you address the chat box to everyone. Otherwise, Greg won't be able to see it. If you're addressing it to me, address it to everyone in that chat box, and I'll stop from time to time. And Greg is a great help to me, so I can stay focused on what I'm doing and not have to go and switch my screen and look in the chat box and read things. And I find it very helpful to have this stuff read to me. It's a great help to me as the teacher. I will try to finish our class a few minutes early, where we'll open up, unmute everybody. People can unmute themselves as they like, and just ask questions. And I'm happy to stay for as long, to answer whatever questions we have coming out of the end of class. Please don't feel any obligation to stay any longer than you're comfortable. I don't want to keep anybody. People, I know everyone's very, very busy, but I will open the class for questions, and I'm happy to stay as long as there are questions that are outstanding. Okay, so let's get to the atomic hypothesis. Here's a very famous picture of John Dalton with his image of the various elements that he recognized at the turn of 1800. And you can see some of the elements certainly that we recognize. The first one there is oxygen and then hydrogen. Down below, he has his compounds that are made up of combinations of atoms as he saw them. Didn't get most of these right. Got very few of them right. If you take a look down the very, very bottom there, we have ethylene. He has ethylene as one hydrogen and one carbon. In fact, it's not, it's C2H4. There's methane right next to it. He has one carbon and two hydrogen. No, methane, in fact, is CH4. Problem here is with atomic weights, relative atomic weights, very difficult in Dalton's day to get the weights of these individual elements correct, to be able to break down the compounds into their various elements with their various weights, their ratio of weights correct. Very difficult to get the data right, and therefore these numbers were all over the map, and therefore very difficult, even with the idea of the atomic hypothesis in your mind, difficult to piece this together correctly. We will see who is the great figure who will fix this problem so that the atomic hypothesis can continue on. We all know that the idea of atoms begins with the Greeks, with Democritus, this idea that matter is in fact made of a bucket of sand. That if you cut it continually, we'll get down to a point where you can't cut matter anymore. You come down to what he called an atom. And it had no parts to it. It was not breakable. It was whatever it was. And various different atoms were of different weights, different shapes, different geometric shapes, but they had an integrity to them which could not be broken. This is the original Greek hypothesis of the atom. We're a long, long way from that when we think about protons and electrons and quarks and leptons. Yeah, we're a long way from the uncuttable atom. Turns out that people believed in atoms long before the atomic hypothesis put forth formally by Dalton. Galileo, Newton, Robert Boyle, one of the great chemists who was a contemporary of Newton, believed in atoms. Boyle studied gases, and his property of gases, which he studied, very much suggested to him the atomic hypothesis, that matter, in fact, was made up of individual particles of matter, of atoms. You remember from high school chemistry, Boyle's law. Boyle's law is a study at constant temperature of the relationship between pressure and volume in a gas. On the left, you see a large volume and therefore a low pressure. But if you'd multiply the pressure and the volume, you would get a certain number. Here, those numbers would give 100. If you were to compress that gas and make the volume much lower, the pressure would go up. However, although the volume would go down and the pressure would go up, the product of those two numbers would be the same as the first one, as long as we kept the temperature the same. And this is the essence of Boyle's law, one of the first of the laws of chemistry. What this shows is that atoms can be squeezed together, that gases can be squeezed together, but still hold on to their inherent property, for example, of Boyle's law. This suggests the atomic hypothesis. The work of Lavoisier, one of the founders of modern chemistry, okay, the person who made the balance beam, the measuring of mass accurately, a centerpiece of chemistry, and in fact of physical science in general. When he showed that when you decompose something, for example, just burning wood, he's the one who realized that it took oxygen to burn anything, that burning was a combination of that fuel and oxygen. When he captured everything coming from that burning, including the gases being given off, when you captured everything in a closed environment and weighed both sides, you found, to his best accuracy as he could find, that you lost no mass, that all the mass could be accounted for. come to be called the conservation of mass, also something which suggests that these things are made up of atoms and they're being just rearranged, that nothing is being lost, they're just being rearranged. Another big piece which would support the atomic hypothesis was the law of composition, constant composition. That is, if you took an element, a compound, and broke it up into its constituent elements, you found that the weight of the two constituent elements were always in the same ratio, always. For example, if you have an element like, a compound like ferric oxide, where the chemist could break up into two known elements, iron and oxygen, they found that if you were able to break that up successfully and measure the weight successfully of those two constituents, that the weight of the iron and the weight of the oxygen was always in the same ratio of 7:3. 70% of the weight was iron, 30% of the weight was oxygen. Didn't matter how big a sample you started with. You always got the same ratio of 7:3 of iron to oxygen. Why would this support the atomic hypothesis? Well, if you believed that atoms all had the same weight, that all atoms of the same element had the same weight, and let me use the example of what real weights are, the weights that were known. If atoms all had the same weight, and if these ferric oxide molecules, compounds, whatever you want to call them at that time, were made up of those two elements, and they had those fixed weights, and they were broken up this way in terms of 2 atoms of iron and 3 atoms of oxygen, then what you would see is the weight of this ferric oxide would be 2 times the weight of iron plus 3 times the weight of oxygen, and the relative weight would be 160, whatever units you're talking about. But if you were to weigh the iron, if the iron had this fixed weight, then 2 times 56 would be the weight of iron, and that weight over the full 160 is indeed 70%. And if you knew the weight of oxygen, 3 oxygens, 3 times 16 over that original 160 would be the 30%. This is not a proof of atoms, this is a classic support of the theory of atoms. That if we had atoms that behaved like this, then the law of constant composition would make sense. There are other ways of explaining the law of constant composition for sure, but the atomic hypothesis certainly is one of them. But the thing that really got Dalton started on his atomic theory, which really convinced him of his atomic theory and why he then pursued it, was the law of multiple proportions, as it's called. He was not the first one to see it, but he's the first one who studied it in great detail and who promulgated it and who used it as support, important support for his atomic theory, which we're coming to, I think, in the next slide. Have patience. What it says is if you have 2 elements, A and B, and you can make 2 different kinds of compounds with them. Take some of element A and combine it with element B in one way, and take that same amount of element A and combine it with element B in another way. What you'll find is if you use the same amount of element A to make this compound, you will use up element B in 2 different ways in which the ratio of the amount of element B being used is always in small whole numbers. This is quite striking. This is very different from physical science as was known up until this time of 1805. Let me give an example before I say that again. Let's take, we want to build up 2 gases, carbon monoxide and carbon dioxide. We'll start with a certain amount of carbon and burn up that carbon, and how much oxygen will be used to create carbon monoxide. How much oxygen do we need to use up all that carbon to create carbon dioxide? What was found was the amount of oxygen needed for carbon monoxide was exactly half the amount of oxygen needed for carbon dioxide. This is very, very strange that this ratio is simply in 1 to 2 whole numbers. You don't see whole numbers in Newton's law of gravity. You don't see it whole numbers in his law of laws of motion, in Boyle's law. You don't see whole numbers. These are all continuous quantities. This is the first time really we see integers introduced into physical science. This is telling us something. This is telling us there's some kind of units involved here. This is what so much convinced Dalton of this idea of the atomic hypothesis. Again, two other oxygen components of sulfur dioxide, sulfur trioxide, having the same kind of thing. The ratio of oxygen that you're using by weight would be 2 to 3. Notice you need to be able to measure these weights accurately if you're going to be able to demonstrate this kind of support. Not easy to do in Dalton's time. Some elements could be done easily, some could not. Okay, what is Dalton's atomic hypothesis? What is the atomic theory? That all matter is made up of atoms, that all atoms of any particular element are identical in size and in mass or weight, and different elements have different sizes and masses, and of course, therefore, different chemical properties. Atoms can only be subdivided. Atoms cannot be subdivided. They can only be created, they can't be created or destroyed. Very much from the Greek hypothesis. Atoms cannot be subdivided, nor created, nor destroyed. In chemical reactions, atoms can only be combined or separated or rearranged. And so therefore, we have the conservation of mass would support this hypothesis. Atoms of different elements combine in simple whole numbers. Yeah, that would be a consequence of those assumptions up above. Okay, that the amount and mass of elements made up in compounds are only in ratios of simple whole numbers. That would immediately come out of the atomic hypothesis. And so therefore, the empirical findings of the law of constant composition and multiple portions support the atomic hypothesis. Again, not proof, but we're now getting into very, very strong support. A number of different empirical results that we see all support the same hypothesis. Take just a look for a second at Dalton's, a piece of Dalton's elements there. You can see two elements of his, which are not elements, soda and potash. Okay? They are, in fact, compounds themselves. Soda is sodium carbonate and potash is potassium carbonate. So in Dalton's time, he could not separate them. He did not know how to separate those compounds and thought of them as elements, just as hydrogen or oxygen. He does have some compounds, gets all of them wrong. Okay, there's the carbon monoxide and carbon dioxide. Those he got right. There's one carbon and one oxygen, one carbon, two oxygen. He got those right, but all the other ones are wrong. He didn't even get water right. Water, he has an oxygen and a hydrogen. Didn't even get water right. Ammonia, he has a nitrogen and one hydrogen, not 4. In sulfuric acid, he has a sulfur and 3 oxygen, no hydrogen at all. Difficult, very difficult to break down these into the proper relative weights so you could see just how many atoms, if you believed in atoms, how many atoms were involved in these compounds. You had to be able to break down the compounds into their separate elements cleanly and then find their relative atomic weights cleanly. Very, very difficult to do in Dalton's day. Other supporting evidence, working with gases and volumes of gases. Gay-Lussac showed that when you combine hydrogen and oxygen gas, discovered by then, by Priestley and Lavoisier and others, you could combine those to create water, big explosion. And what he found was it took 2 volumes of hydrogen for every volume of oxygen to consume all that oxygen to produce 2 volumes of steam. Okay? Again, here is a law of combining of constant proportions, but now in volumes as opposed to weights. When electrolysis came along, and we'll talk about electrolysis a bit in a moment, when you could use electricity to break up compounds into their elements by running electricity through them, he found the exact opposite. He found that when you broke down water, for every volume of oxygen that was created in the dissociation, 2 volumes of hydrogen were created. So in fact, this process went both ways. So we had a law of constant proportions, now not by weight, but by volume, which of course would be proportional perhaps to weight if you believed in the atomic hypothesis. More supporting evidence. A very big one was when electrolysis was brought to the fore, was Faraday's law of electrolysis, where if you ran a certain amount of electricity through a molten salt solution, for example, where you had on the various cathodes and anodes, all names, by the way, all coined by Faraday, electrolytes, electrodes, all these words coined by Faraday, the greatest experimental physicist, perhaps of all time, certainly of the 19th century. That he found that one element would collect on the cathode, the negative terminal, and one element would collect on the positive anode. Here we have simple salt collecting the sodium and the chlorine on the two different anode and cathode. And what he found was no matter how much electricity he ran through, when he stopped the current and could measure accurately, which he could do better in the 1830s, how much sodium did accumulate on the cathode and how much chlorine gas was given off and collected from the anode. What he found was those weights that he collected was the ratio of those weights was exactly in proportion to the actual relative weights of the elements themselves. If you knew what those weights were, where we were getting better and better at doing that. So the relative weights of sodium and chlorine was 23 to 35.5, and sure enough, if you stopped the electrolysis process, when you got 23 grams, for example, of sodium, you found you collected 35.5 grams of chlorine gas. If you stopped halfway through and only got half of that amount of sodium, you only collected half amount of the weight of chlorine, etc., etc. That you always collected the amount of the element in the proportion of their weights 1 to 1. This told us if you believed in the atomic hypothesis that salt, this salt compound, was divided in some way equally between an atom of sodium and an atom of chlorine. Because when you broke them apart, you saw this separation in weight. So we come to the fellow who did finally show us how to find accurately atomic weights. We need this. We're waiting for Berzelius to develop the new techniques to break up compounds into their constituent parts cleanly, and then to find ways to measure their relative weights. He is considered one of the founders, not only one of the founders of modern chemistry, along with Dalton and Lavoisier, he is probably the central figure of the first half of the 19th century in terms of the most important chemist that we have. He developed, for example, our modern chemical system of H2O being water, two atoms of hydrogen and 1 of oxygen. He discovered a number of elements himself through his new techniques. He was the one who perfected the use of electrolysis and other techniques of his own invention to be able to break up compounds cleanly into their constituent pieces, collect them cleanly, and be able to find a way to measure their relative weights. He began with using the relative weight of oxygen as 100, and then measured things relative to how much oxygen he was able to collect. Nowadays, we don't use that. We use the isotope of carbon-12 as our fundamental unit for chemical weights. But the basic idea has remained the same as what Berzelius does. Once we have accurate atomic weights going for us, now the atomic hypothesis can take off, okay? Now, as we see chemical elements coming into families, here we have the two probably most famous families, the extreme left-hand column of the periodic table, all the different metals, lithium, sodium, potassium, and the next to last column to the right, the halogens, fluorine, chlorine, bromine. Okay. Once you see that these elements have very, very common chemical properties, they were naturally put into families of elements long before the periodic table was developed. But I asked you just to look at the dates for a moment. Look at these dates: 1817, 1807, 1807, and then fluorine 1810, and even bromine 1825, iodine 1811. This is the heyday of electrolysis. This is where so many elements were discovered with the process of electrolysis. Berzelius was one, Humphrey Davy in London, the mentor of Faraday, another, discovered many, many elements. And in fact, between 1800 and 1865, the number of elements known was doubled during that time. And it was very much through the techniques of Berzelius, being able to separate things cleanly. And one of those very, very important techniques was the electrolysis of running a current through some kind of a liquid solution in which the various individual elements could collect on the electrons. So with those elements, the stage is set for Mendeleev. And I did hope you got a chance to watch that very short video that I asked you to take a look at on the development of the periodic table. What he did was he basically wrote down the elements on index cards with their weights. Now that these weights were known, he also discovered a number of weights himself. He had to his credit. And he tried to make sense of these families by laying down these cards almost like in solitaire to see if he could find some kind of a pattern besides just the families that were known. And this is a prototype of his first periodic table of around 1870. And what he's doing, he's simply laying down the elements by their weights, putting them in order, but keeping a close eye on the chemical properties, making sure that sodium has to go under lithium. He's not going to put sodium here. Yes, true, 23 comes after 19 in the weight that's known, but he can't put it here because he knows that sodium is in the same family. So by watching the order of the weights and by keeping a very close eye on his chemical properties, he develops this table. Quite remarkable. What he does, perhaps even more remarkable, he leaves holes in his table, okay? He knows that he's not going to put titanium here. Titanium is not similar to aluminum, okay? Titanium is similar to silicon and carbon. He leaves a hole here because, again, he knows that this element, this element here, he leaves two holes. He knows that arsenic is not similar to this column of titanium or silicon or aluminum and boron. He knows that arsenic is much more similar in its chemical properties to phosphorus and nitrogen. That's why he knows to leave these holes. Not because the weights are so wide, although that's a clue, it's because they don't fit the chemical properties that he feels now is developing in his columns. And in fact, we know, and the videos so well pointed that out, over time, people began to fill in these holes with just the weights and properties that he predicted. These various different elements were discovered. By 1898, we had this thing beginning to look like the modern periodic table, the noble gases. the final column was discovered here in the late 1890s, particularly in 1898, by Sir William Ramsay and his team in London. And this pretty much flushed out the periodic table as we know it. This, of course, is today's periodic table. For example, we have all kinds of elements above 92. This is our last uranium, our last natural element. These are all synthetically made elements going beyond here and all beyond here. So here in 1898, let's certainly take away those. Those were not even thought of. And there were some holes. There were still many holes in the periodic table. Some of them anticipated, some of them not anticipated. Many of these were anticipated. Some of these tricky guys down here were not anticipated because these elements were not well understood what was going on. But there were holes to fill in, and the studies of radioactivity certainly helped to fill in many of them. Here's a good example of an 1898 polonium was discovered by the Curies, named after her homeland in Poland. And of course, radium was discovered and to be very powerfully radioactive. So we have the periodic table as we now understand it today. Okay, before we finish off our story of finally the chemist believing in atoms, Greg, any questions pending?
Yes, we have some observations and a bunch of questions.
Good, observations are always good too.
Joe Parisi says, just an observation, given the difference between the size of protons, electrons, etc., and the radius, an atom is primarily empty space.
That's for sure. That is one of the great things which is pointed out very often. Thank you, Joe, for pointing that out. I was very remiss in pointing that out, that when we're looking at the radius is one thing, looking at the volumes of things, what Rutherford found was that the volume of the nucleus is absolutely tiny compared to the overall volume of the atom, where the electron is what he thought surrounding, going outside. The typical analogy that is done, that you'll see very often, certainly in one of the videos that I'll suggest, says this: if you think of it as a football stadium, if you think of the atom as a football stadium, the nucleus is a grain of sand on home plate. That is an accurate relative measure. What else we got?
Brad Roscoe says, in practice, making a chemical reaction work to provide only one end product is difficult. How did they do the carbon oxidizing experiment and ensure that they only got carbon monoxide or carbon dioxide and not a mixture?
I was worried that someone would ask me a question like that. In all fairness, you have to understand and realize you are asking for a course in chemistry. To go into that, as fascinating as it is, there is no easy answer to that. That is the whole life's work of Berzelius and the people of his generation. Okay, the ingenious chemistry that was invented, discovered to do those things. So no, we have no ability to go into that. But boy, that is such a fascinating question of how the atomic weight problem was in fact truly solved by Berzelius. The little video that I suggested to watch more about his life really doesn't go into that. But if you want to go into the history of 19th century chemistry, that is where you will find that, and it is truly a fascinating story. There are a number of great books on the history of chemistry. A very famous classic is called The Crucible, which I can recommend. A wonderful narrative story which goes into questions like that. Okay, let me finish up. I'm running out of time. Let me finish up the presentation here, and hopefully at the end we can get through some more questions. So the great synthesis of Newton's laws really culminated in our understanding of the law of gases. And from the law of gases, we came to understand the meaning of heat, heat being the motion of molecules, and therefore of the laws of thermodynamics. Okay, these were well understood by the 1880s. The great names here are Maxwell and Boltzmann. This is what convinced physicists of the atomic hypothesis. There's almost no way to understand the laws of thermodynamics and the laws of gases way beyond Boyle's law, the universal gas law, etc. There's almost no way to understand those without the model in your head of these individual molecules moving around, bouncing around, knocking off of each other in Newtonian ways, creating pressure, creating what we can measure as what we call temperature, simply the average kinetic energy of these molecules being the energy of heat that we can measure in temperature. There's no way to do this without having the atomic model as your fundamental basis. But chemists, still, many chemists could still, nice fiction, very useful to answer some kinds of questions, but not needed for many other kinds of chemical reactions that I'm concerned with. So it was in this vein here, looking at the Newtonian mechanics and thermodynamics, where finally we get the convincing argument that even brought the final chemists along. And that was done with an observation going way back to the 1820s of a doctor, Robert Brown, who noticed what we now call Brownian motion, where a very small particle, he had pollen grains in water, and under a microscope, they just kind of bounced around in a random kind of way. And some people at times said, oh, that's because maybe they're alive. He did a very clever thing. He ground up glass into very, very fine powder, put that into the water, and they also bounced around. So no, it wasn't because they were alive. They were being pushed around, I guess, in some way. But liquids at the time, certainly of Brown and further on with these reluctant chemists, liquids were continuous. They were that bucket of molasses. They were not necessarily atoms. Yeah, the physicists were having their field day with the gases, but no, when you came to liquids and solids, not necessarily true. But yet it looked like they were being knocked around, but they just looked like that. Someone had to come along and convince us that this was in fact the case. And some of you may be surprised that the guy who did that was a young patent clerk in Bern, Switzerland, called Albert Einstein, who hadn't yet had his PhD thesis approved yet by his university, able to get a job by the father of a friend. And he published a bunch of articles in 1905, and this was one of them, where he developed this model. Einstein is a master of statistical mechanics, a master of statistical and probabilistic arguments, which he will use very, very well later in his career, as we'll see. That he makes a model of, in fact, that the liquid water acts, in fact, like a gas. That the molecules of water act just like the models of Maxwell and Boltzmann. And they will knock around these particles because they have an individual life to them, an individual motion. And he creates this statistical model and in fact makes a prediction of how these larger molecules would move. And all it takes is for someone to come along and in fact show that's the case. And the great experimental physicist Jean Perrin, who won the Nobel Prize in 1926 for exactly this work, showed experimentally the truth of Einstein's model. Okay? And if Einstein, guys, had done nothing else but this, he would be in the history books. Yes, he would be attached forevermore to Perrin's name, that Perrin would be the greater name, that this young physicist created a model which Perrin then showed to be true, but he would be in the history books to show finally, definitively, the evidence for atoms in liquids and therefore atoms in general. And no one could put it better than the great Wilhelm Oswald, the great physical chemist of the early 19th century, one of the grandfathers of modern chemistry, founder with people like Ernest Nernst, all the great chemists of this time. I have convinced myself, finally, that we have recently come upon possession of experimental proof of the discrete or grainy nature of matter, for which the atomic hypothesis has vainly sought for centuries, even millennia. Okay. Do we have any other questions, Greg, from the chat box before I open up questions?
Yes, yes, Peter, we've got a bunch. From Jim Talbert, how did Guy Lussac obtain pure hydrogen and pure oxygen?
You do that. Electrolysis is pretty easy. You might remember that from high school chemistry. You set up two electrodes with water. You put a little salt in there so it'll carry the current. And under the right circumstances, you will have bubbling up the hydrogen ions, which are positively charged, will go towards the cathode, and hydrogen gas will form on one, and you'll be able to collect that in a container up above. And the oxygen atoms will float, which are negatively charged, will float towards the anode, which is positively charged, and it will float up, and you'll be able to collect the oxygen. And you can do this actually quite cleanly. This is a very easily done experiment from high school chemistry. So shame on you, Jim, that you don't remember high school chemistry from years ago. What else do we have?
Mary Covington asks, how did Dalton weigh the elements?
Again, you guys are asking me the same question. This is the intriguing question. I absolutely get it, guys. This is what's fascinating, okay? How this was actually done through the techniques of early chemistry. Basically, what was done was certainly the electrolysis, once you could collect these gases, which were done really in the 1820s and so, it got easier because you could go ahead and weigh the amount of gas that was collected. Before that, what used to be done was you would work with gases that you could kind of vaporize elements and create them into gases, and then find a way to separate the gases using through heat. Very often you could burn a gas. You could burn, for example, methane gas, and you could deposit, the burning of the gas would deposit the sulfur onto a surface, and you could try to collect all the sulfur from the surface and blah, blah, blah. This is a fascinating question. I agree, guys. I understand. I get it. But this is something that you're going to want to pursue on your own because we're trying to get to quantum theory. All right. Is there anything else on the chat box?
There's a few more questions.
Okay.
Bill Gunther asks a very basic question. Please define a proton and a neutron.
Ah, well, now I don't know if I should do that. I don't know if that's cheating or not altogether. Okay, this of course will be one of the central questions of our whole course. How were these guys discovered? The proton and the neutron live in the nucleus. The proton has a positive charge. The nucleus has no charge at all. What else?
Jim Talbert asks, does electrolysis work only for binary compounds?
No, not at all. You can separate all kinds of things. You can separate the calcinates and all kinds of things. It's a very, very powerful method. As long as you have the compound separated into its charged ions, you can get them to drift towards the different electrodes.
And Arnold has 3 questions. I'll do them one at a time, I guess. Is there a vacuum between atoms?
Yes, good question. Yes.
Is it true that matter cannot be, quote, destroyed?
Well, now that's a complex question. Can we hold that off? because quantum mechanics will have something very profound to say about that. Certainly under the classical laws, no, the answer would be no. We would have the conservation of mass. But we got to modify that once we get to quantum theory.
Third question from Arnold. When you say an element is similar to another element, what constitutes this similarity?
Well, at the first, it was the chemical properties. You take that simplest example of the lithium, sodium, potassium. They all make salts. They all make different salts with the other side, with the chlorines and the fluorines. So they all can make a very similar salt kind of compound. There's an example of a family kind of trait.
Last question from Sharon Beatty. What was financial motivation for supporting research in the 18th and 19th centuries?
Well, that's of course very interesting. You know, in the 18th century, it was mostly done by people of independent means. You'll find that many people were of independent means, or they were supported by their by the court. Certainly going back even, you know, to Newton's day and on. But as the 17th century, 18th century developed, you did begin to have the universities, and you did have professorships where you were paid to teach and paid to do research. And so the universities become more and more the center of research. And certainly that's almost completely true in the 19th century and today. I guess for today, we really need to add industry.
That was the last question, Peter.
Okay, anybody wants to open up? Anybody who's have anything you want to throw out before we go?
Well, government finances research.
Absolutely, government, industry, and university. Absolutely, thank you.
Peter, I have a couple of questions. Can you hear me?
Yes, I can.
Oh, okay, thank you, sorry. Early on in the slideshow, you had various chemical elements, and I'm guessing a diffraction grating that showed the different spectral colorations.
Yes.
Early on. Can you explain why, I think it was the very top one, was that?
Hydrogen.
Hydrogen, yes. That had 3 bands of red in it, whereas others either had none or 1. And then in a couple of others that were in there, there were 2 bands that showed of yellow, and others may have only had 1. And I'm not remembering the order. Is there, what is the reason that, you know, one had 3 red bands? And
I am very happy to explain that. That will be one of the key questions of our entire course. We will answer that question thoroughly. You have gotten to the heart of the discovery of quantum theory.
okay.
Okay, so hang on. We will be talking about that. That is one of the great discoveries that leads to quantum theory, to understand the answer to your question. That is in the Bohr atom.
Okay. And then the second question that I have is much simpler question, I guess. It seemed that from the video that you included on Berzelius, that there were, during that time, all kinds of scientific societies that emerged. I kind of remembered there was.
Oh, sure. The Royal Society is a very important one. The Society in France and in Berlin. Absolutely.
Is that ongoing? Does that occur so much these days, or has it just kind of been reached? And
oh, no, very much so. I mean, they are no longer the centers of research anymore. In those days, they were the center of research. But oh my goodness, no, the Royal Society and its ilk are very much alive and well. And to be part of those organizations are a great prestige in the world of science. Mm-hmm. To be voted a member of those. The whole story of allowing women scientists into those organizations is a whole story in itself, which we'll touch upon when, for example, you know, Marie Curie was finally voted into, you know. So no, these institutions are very much alive and well, but they're no longer centers of research. They're more places where journals are published from, and where conferences are organized out of, and things like that.
Okay, thank you.
All right, guys. Well, this was a great first class. Thank you very much. The recording of this thing will be out by the afternoon, I hope. And look for my next Wednesday email.
Will the recording include the Q&A?
Absolutely. I'm going to shop the recording right now. Everything has been recorded.
Okay, super.
All right, guys. Be well.